Hi everyone, and welcome to this new video about steady-state analysis. We continue with our examples about RLC circuit. This is our example number 5, and in this example I would like to discuss the superposition principle for this circuit, having in this case two voltage sources. And superposition principle is very handy when you have more than one source, so that's actually the situation what we have here. And I would like to apply the superposition principle for this example, and I will illustrate the concept. So what we have is the following. We have the resistor, inductor, and the capacitor, and two voltage sources, VA and VB. And we would like to calculate the steady state current through the resistor R, which is IR as shown here in this direction. Okay, before I start with the actual analysis, I would like to determine the frequency representation of the elements, the inductor and the capacitor, and also the voltage sources, VA and VB. So let's start first with that. So first, what is the X of L? It is the reactance of the inductor, omega times L, which is 200 omega times 0.04, which is 8 ohms. And for X of C, which is 1 over omega times C, which is 1 over 200 times 5 times 10 to the minus 4, which is 10 ohms. So this is actually the radiance frequency, so it's actually this one. This is just 40 millihenries from the inductor, and it's also the same radiant frequency, that's 500 microfarads from the capacitor. So next one is the VA, which is just an vector notation. That will be 5 volts and a phase of minus 25 degrees, units volts. And the next one, VB, will be 2 volts with a phase of plus 40 degrees in volts. If you have in the cosine representation your time function, you can just take over the amplitude and the phase and you place it in this form. If it's a sine function, you have to add minus 90 degrees for your phase. And this is actually also cosine, so you can just take it over. That's actually for this part. What we do for the superposition principle is activating one source at a time and then calculate the effect of that source to, for example, in this case, your resistor current. And then you activate the other source and you also disable all of the sources, so you activate one source at a time. So you activate then the VB, you calculate then the effect of this source on the resistor current, and you add the separate parts together. That will be your total solution, and that's actually the whole business for this superposition principle. So I will first only make active, so only VA active, means VB will be a short. So how does the circuit look like? What is the new situation of the circuit? So what we have is the following. You have the VA still in place, that is active. We have the capacitor. We have the resistor, that's still in place. And we have the inductor, which is actually also going through ground directly because this is a short. So I can make a parallel combination of that, which is this. And this combined impedance I can now use together because I've now designated the point here. What I want is, of course, the current through this resistor R. If I know the voltage at this point P, what I now call P, I can also say that it's the exact same voltage across the resistor R, and then using Ohm's law I can calculate the current. So what I'm actually heading is towards this point, voltage at this point, so VP. So first, before I can do that, I will combine these two elements together and make that, for example, Z of B. So a combined impedance Z of B, P. So it will be Z of P, which is equal to the parallel combination of R and the reactance of the inductor. That will result in J times R times X of L divided by R plus J X of L. If you now substitute the values we have given as R is 6, X of L is 8, you will have J 48 divided by 6 plus J 8. If you now calculate this out, you will have in the polar representation 4.8, phase 37 degrees in ohms. And if you do that also, if you want, also in the representation of the rectangular form, so you will have 3.8 2.83 plus J 2.89. This is also, so actually we have now the impedance ZP. What we have is then the following. This circuit now can be again redrawing, and it can be actually, you can see this one as one impedance, and you can then apply voltage divider rule. So what I do is first make the voltage divider rule here. So V of P will be equal to this impedance divided by the total impedance seen by the voltage source VA. So that will be minus Jx of C plus Z of P times VA, all of course in vectors for vector representation. Now if I continue, I will substitute the value here in the polar representation because I would like to divide out. So I will have 4.8 phase 37 degrees. This will be minus J10. And I will have the ZP in this case in rectangular representation because I would like to add. So it will be 3.83 plus J 2.89. And I will have the VA, and we have already determined that is 5 volts with a phase of minus 25 degrees. So the next step is actually the following. I want this combined with the real part and the imaginary part in a simplified form, and again convert this also in the polar representation. So that's actually the next step. So I will have still 4.8 phase 37 degrees, that's still in place. And if I now reduce this and again convert to the polar representation, I will have 8.08 and a phase of minus 62 degrees. That's for that part. And you will have still the voltage VA is 5 minus 25 degrees. Now what do you do in this case? You have division here and a multiplication there. So what you actually do is if you see a multiplication, you multiply the amplitudes. If you see a division, you will divide the amplitudes. If you see a multiplication for the phases, you add them up. And you see a division, you subtract the phases. So you will actually have the following: 4.8 divided by 8.08 times 5. That's actually our amplitude. In total, that will be 2.97, and our phase will be 37 minus 62 plus minus 25. And it will be, in this case, 474. And that's just in volts. And this is also the voltage across the resistor, because it's parallel. So I can now continue and calculating the resistor current here flowing in this direction. So actually I have now this current, we'll make it in red. So this current flowing in this direction, of course due to only VA, I can now calculate that. So if I now continue here, so what is the current? So the current will be IR will be VR divided by the R itself. So that will be IR is 2.97 phase 74 degrees divided by the resistor was 6 ohms, and there's a phase orientation of 0 degrees. So if I now also use that, that will be for this part will be 0.495 phase 74 degrees in amperes. That is actually, this one is only due to VA only. Okay. So we have actually one of the parameters. Let's also represent this in the rectangular form. That will also be handy when we carry out the calculation. So what is the representation of this form? So in the rectangular expression. So if you now use the formula for, I will continue in black. So what do I have is the following: IR is 0.495 will be cosine of the 74 degrees plus J sine of 74 degrees. If you now do the math here, you just calculate the cosine of 74 and then also the sine of the 74, so you will multiply that also with that 0.495. So you will have for the first one, that will be, this one will be 0.136 and then plus the other one will be again same, but then you use the sine, it will be J 0.476. And again, this is just in amperes, so we have actually the representation both in polar and the rectangular form. So I will use this in the final result. So if I now continue with the calculation for only VB, so I'm done actually for VA. So what is actually VB only active? If this is only active and this is disabled, this will be a short. So I will see then the C and the R as a parallel form, and then I will see the first inductor and then the parallel form of the capacitor and the resistor. So let's move on with only active VB, so only VB active. So the circuit will be like this. So we have the short here. So, or I make this directly the capacitor in parallel. That's a bit handy. So I have the capacitor here, which is in parallel already with the resistor. And I have the inductor, which is connected now to VB. Again, the same procedure I can apply here. I can say, okay, this point, what I have here, can be again designated as point P. And I have now this complete impedance here. And I will now use that to determine the new impedance, and I will use again the voltage divider rule. So if I now designate this as Z2, just different from ZP, of course. So what we have is then Z2 will be parallel combination of R and minus J X of C, and this will be minus J times R times X of C divided by R minus J X of C will be minus, if you now calculate R times X of C, R was 6 and X of C was already calculated as 10, it will be minus J60. This will give you divided by 6 minus J10. Again, do the math here, it's very simple, I've already discussed it in previous videos, from converting from the polar representation to rectangular and then also the other way around. You will have in the polar representation 5.15, phase of minus 31 degrees ohms, and if you want also in the rectangular representation will be 4.41 minus J 2.65. Okay, now if I now use the voltage divider rule, I will now calculate this point for the voltage. So if I now use VP, why do I need the voltage? Why do I require all voltage, or why I'm heading to that voltage? Because if I know the voltage again at this point, I can now use also for this resistor again the Ohm's law. I can calculate the current for this situation, for this IR due to VB. Okay, if I now continue, it will be Z of 2 divided by JXL plus Z2 times VB. So Z2 is given in the polar representation 5.15 minus 31 degrees divided by J, and we have already calculated the inductor, which was 8, so J8 plus 4.41 minus J 2.65, and then times the voltage VB, which is 2 volts phase 40 degrees. Now again, we combine the real parts and the imaginary parts here together, simplify this, convert the polar representation, and you divide everything out, and you will have your final result for your voltage VP. So this will be, I will show that in additional steps. So 5.15 phase minus 31 degrees divided by, so this one, for this rectangular representation, I will have a phasor representation of the polar representation of 6.93 phase 51 degrees, and then 2 phase 40 degrees. If you combine all those terms, you will have, for the VP, this will be 1.49 and a phase of minus 42 degrees in volts. Now, of course, this is also equal to VR. Again, because this is in parallel. So VP, what I have here, is the same as the voltage across the resistor R. Then I can say the following. Now the IR, due to, of course, only VB, is VR again divided by R. And VR in this case is 1.49 phase minus 42 degrees. So, and divided by the same resistor, which is already given in the examples, which is 6 in a phase of 0 degrees. And this will result in 0.248 in a phase of minus 42 degrees in amperes. Okay, now I'm actually almost done. So the total effect, that's actually one. I have now the current. So due to VB only is also given. So the net effect of total effect, total solution, so total solution will be, of course, IR, total will be IR due to VA plus IR due to VB. That's actually the situation here. So if I now write down the expressions for IRVA and IR due to VB, which is shown here, I have this, so 0.495 phase 74 degrees. I will also take this and I will add them up. So what do I have? The following: 0.495 and a phase of 74 degrees plus 0.248 phase minus 42 degrees. So what you do is, again, we have a polar representation, so adding in this form is not really handy, so we have to convert this and also this in the rectangular representation, and then add the real parts and the imaginary parts, and then combine again back to the polar representation, and then transform, that's actually our final step, to the time domain. So if I now do that also, so what you do is very straightforward. You will take again the same formula. You will have the amplitude, so for the first one, time its cosine of the phase plus j sine of that phase, and then plus the second amplitude will be 0.248 times now the sine of the minus 42 degrees, I mean cosine, excuse me, this will be cosine of minus 42 degrees, and then plus j sine minus 42 degrees. So we have this, as you can see, cosine of 74, sine of 74, and then cosine of minus 42 degrees, and also sine of minus 42 degrees. And then you multiply each of these terms with its own amplitude. Now, if you now work this out, you will have in total 0. For the real parts, you have 0.321, and for the imaginary part, you will have plus j 0.31. It's of course in amperes, and I would like to convert this to the polar representation. How do I do that? Let me also make this clear here in this example. This will be the length of this vector, so that will be the square of the real part and the square of the imaginary part, and also the arctangent of the imaginary part divided by the real part. And this will give us the phase and the magnitude of the vector representation of the IR. So this will be IR is equal to 0.446 and a phase of 42 4 degrees in amperes. Now I'm now almost done because I would like to go from this to the time domain. So I will have to transform back to time domain. So what is the time domain representation here? So IR in time will be again the cosine. That's just a template. What we have was cosine and a 200t, remember, and we have the amperes. For this part will be the amplitude, so you will write down what you have here, 0.446, you will have to place it here, and the phase of 44 will be placed here, so it will be plus 44 degrees, and the amplitude will be 0.446, here plus. And that's actually for this example, so you know the net effect of your system by dividing your complex system, actually in this case, into very simple circuits, and you calculate the separate effects only due to VA and only due to VB, and then combine them together linearly because it's a linear system, and you add them up and you transform back to time domain. That's actually the whole business here. Okay, so that's actually for this example, and take care and see you next time.